So this is Linear Algebra Lecture 7, and we're talking now about Chapter 2, which is on matrices. So if you think that a column vector in Rn, or maybe I should say Rm, is a column with m numbers, x1 up to xm. So here we have one column. You can think of this as m rows, but just one column. And we generalize this to a matrix. So for positive integers m and n, an m by n matrix is a rectangular array of scalars, numbers, with m rows and n columns. For example, a 2 by 3 matrix, an example is 1, 2, 3, 4, 5, 6. So if you look at this, you have m equal 2 rows, n equal 3 columns. A 3 by 2 matrix, an example, is 1, 2, 3, 4, 5, 6. So this has m equal 3 rows. Let me call this B. And n equal to 2 columns, and A is different from B, right? Right? Two matrices are the same if they had the same number of rows and columns and the same number of coordinates of scalars or numbers in each place. So the general notation, if A is an m by n matrix, we might write for short A equals Aij. And what this means is, this is the matrix. The first row is A11, A12, say A1j up to A1n. Second row will be A21, A22, A2j up to A2n. The ith row would be AI1, AI2, Aij up to AIN, down to the last row, the mth row, AM1, AM2, AMJ up to AMN. So this is the ith row of the matrix. And in fact, we might say row sub I of A is just this row vector, AI1, AI2, up to AIN. And this is the jth column of the matrix. So I'm right, column sub j of A is this column, A1j, A2j, down to AMJ. And Aij always denotes the scalar, the coordinate. So this is the coordinate in row I, column J. So this is standard notation for matrices in our class and everywhere else. And there is a kind of elementary algebra of matrices. You can add matrices of the same shape. That is m rows, n columns. You cannot add matrices of different shapes. But if you have, for example, 2, 0, minus 1, 5, 4, 7, so this is a 2 by 3 matrix, and 8, 1, minus 1, 2, minus 5, 3. You add them. By adding, so they're both 2 by 3 matrices. They have the same shape. If matrices do not have the same shape, you cannot add them. But you add them by adding the coordinates. This is the first row, first column coordinate. First row, first column coordinate. 2 plus 8 is 10. First row, second column, first row, second column, 0 plus 1 is 1. First row, third column, first row, third column, minus 1 is minus 2. And similarly, you get 5 plus 2 is 7. 4 minus 5 is minus 1. 7 plus 3 is 10. Again, it's a 2 by 3 matrix. And you can also scale or multiply any matrix. You just multiply every coordinate by the scalar. So 3 times 2, 0, minus 1, 5, 4, 7. You multiply every coordinate by 3, you get 6, 0, minus 3, 15, 12, 21. If you wanted this in symbols, if A is the matrix Aij, and B is the matrix Bij, and they're both m by n matrices, then A plus B is the matrix whose ijth coordinate is just the sum Aij plus Bij for all I and j. And C times A is the matrix whose ijth coordinate is C times Aij for all I and j. So these two rules describe addition of matrices and scalar multiplication of matrices. So sometimes you might write capital M sub mn is the set of all m by n matrices. And in fact, with these operations, this is an example, another example of a vector space. So the vectors, the elements, are the m by n matrices. This is vector addition, this is scalar multiplication. And all the properties of a metric space, of a vector space, are satisfied. Okay? Any questions about that? What's the zero element? You have the zero matrix called ZMN, and this is just the matrix where every coordinate is 0. And any matrix A plus the 0 matrix is just A, which you're just adding 0 to all the coordinates. Okay. Now, matrices have another property that's a tad more complicated, and which is matrix multiplication. And in general, if you had, for example, 2 by 3 matrices, here was an example. These are 2 by 3 matrices. This one and this one. There's no way to, the multiplication of these matrices is not defined. You cannot necessarily multiply matrices of the same shape. So matrix multiplication is a little more complicated, and matrix multiplication is possible in the following case. Suppose A is an m by n matrix. Aij. So m rows, n columns. And suppose B is a matrix which has n rows and p columns, so an n by p matrix, Bij. So this has n rows and p columns. Now, the important thing here is the number of columns in A equals the number of rows in B. And in that case, it is possible to multiply, right? So we define a matrix A times B equal to C with coordinates Cij as follows. And maybe I'll start with an example just to make it clear. Suppose I have, for example, A is a 2 by 3 matrix. 1, 2, 3, 4, 5, 6. And B, so this is 2 by 3. And maybe B is 3 by 2. 2, 1, 4, minus 1, 3, 7. So here, the number of columns is 3. Here, the number of rows is 3. So there's a way to multiply these matrices. A times B, 1, 2, 3, 4, 5, 6, times the matrix 2, 1, 4, minus 1, 3, 7. And the rule for matrix multiplication is you multiply a row times a column. So suppose you have a row, for example, 1, 2, 3. And you have a column, 2, 1, 4. So they have the same number of scalars. Here we have 3 horizontal numbers. Here we have 3 vertical numbers. And you just take the first coordinate in each, 1 times 2. The second coordinate in each, 2 times 1. The third coordinate in each, 3 times 4, and you add it up. This is 2 plus 2 plus 12, so this is 16. So the number you get when you multiply this row and this column is 16. And that's how we define matrix multiplication. If you want to know, so this is m rows, n columns, this is n columns and p rows. The product C, AB equals C, will have m rows and p columns. This will be n times p. So here m is 2 and p is 2. This will be a 2 by 2 matrix. This is 2 by 3, 3 by 2, and the product will be 2 by 2. And to find the coordinate that goes in the product, first row, first column, you multiply the first row by the first column. That's what I did here, and I got 16. What goes here? This is the first row, second column. So I multiply the first row by the second column. I get minus 1 plus 6 is 5 plus 21 is 26. This is the second row, first column. So I multiply the second row into the first column. 2 by 4 is 8 plus 5 times 1, that's 5, that's 13. 6, 4 is 24, 13 plus 24 is 37. And this is the second row, second column. So I multiply the second row into the second column. I get minus 4 plus 15, that's minus 11. Minus 4 plus 15 is 11, plus 42 is 53. So the product of these two matrices is this. Right? So this is matrix algebra. It's very, very important that you learn how to calculate these products. Okay. Let's look at a few more examples. Suppose I take a simpler case. Suppose A is the matrix 3 minus 1, 5, 0. And B is the matrix. I'm just making up numbers. 2, 7, minus 9, 8. So A times, so this is 2 by 2. This is 2 by 2. So the number of columns here is the number of rows here, and I can multiply them, and the result will be a 2 by 2 matrix. So let's calculate it. First row, first column. Take the first row into the first column. 3 minus 1, 2 minus 9. That's 6 plus 9, that's 15. First row, second column. 21 minus 8 is 13. Second row, first column. 5, 0 into this is 10. Second row, second column, this times this is 35. So this is the matrix AB. I can actually multiply in the opposite order. BA, again, because this is 2 by 2 and this is 2 by 2. So B is 2, 7 minus 9, 8 times the matrix A, 3 minus 1, 5, 0. So this is again a 2 by 2 matrix. First row, first column, 6 plus 35 is 41. First row, second column, minus 2 plus 0 is minus 2. Second row, first column, minus 27 plus 40 is 13. Second row, second column is 9. And now we see something which is absolutely critical to always keep in mind. This is AB. This is BA. In this example, AB is not equal to BA. Give that a star because that's important. So matrix multiplication, when it's defined in both ways, is not commutative. It's not the case that AB equals BA. They are, in a special case, it may happen they're the same, but in general, they're different. So you can never assume that AB equals BA. This is not the case. All right. Okay. I just want to add one other remark, which is useful. We'll see it later. There's an operation on a matrix called transposition. So the transpose of a matrix of an M by N matrix A is the matrix, and it's going to, instead of M rows and N columns, it's going to be reversed. N times M matrix obtained, the M by N matrix called A superscript T. That's our notation. Obtained by interchanging rows and columns. And what that means is the following. Suppose A is the matrix 7 minus 1, 8, 3, 2, minus 5. So what is A transpose? This is a 2 by 3 matrix. A transpose will be a 3 by 2 matrix. And by interchanging the rows and columns, I mean the first row of A becomes the first column of its transpose. The second row of A is the second column of the transpose. Or you could look at it differently. The first column of A is the first row of A transpose. The second column of A is the second row of A transpose. the third column of A is the third row of A transpose. It's exactly the same thing. So if A is the matrix Aij, and A transpose, I'll write it as Aij superscript T, the ijth component of the transpose is the jith component of A. That's a kind of symbolic way to write this. But the first thing to remember is you transpose a matrix by interchanging the rows and columns. Right? And this will turn out to be, it's a very, very simple operation. It'll turn out to be useful later. I should make one other remark, because in general, you can't necessarily multiply matrices A, B in the opposite order, BA. Or you can, but something strange happens. So suppose A is a 2 by 3 matrix, and B is a 3 by 2 matrix. So then A times B, 2 times 3, 3 times 2, this is going to be a matrix which is a 2 by 2 matrix. But if you take BA, B is 3 by 2 and A is 2 by 3, this will be a 3 by 3 matrix. So A, B, and BA are both defined, but they have completely different shapes. Right? Let's see. I actually did an example before. Here is the matrix A, here's the matrix B, and A times B was this 2 by 2 matrix. Right? Suppose I had multiplied B times A. So B is 2, 1, 4, minus 1, 3, 7, and A is 1, 2, 3, 4, 5, 6. This is going to be a 3 by 3 matrix, not a 2 by 2 matrix. First row, first column, this times this is 2 minus 4 is minus 2. First row, second column, 4 minus 5 is minus 1. First row, third column is 6 minus 6 is 0. Second row, first column, 1 plus 12 is 13. Second row, second column, 2 plus 15 is 17. Second row, third column, 3 plus 18 is 21. Third row, first column, 4 plus 28 is 32. Third row, second column, 8 plus 35 is 43. Third row, third column, 12 plus 42 is 54. So here I have a 2 by 3 matrix and a 3 by 2 matrix. The multiplication AB is defined, I get a 2 by 2 matrix. The multiplication B times A is defined, but I get a matrix of a completely different shape, as 3 by 3. Right? So this is something you have to keep in mind. Now, there's one case when A, B, and BA are defined, and you get matrices of the same shape, and that's when you have what is called a square matrix. A square matrix, a rectangle you think of as looking like this. Square looks like that. A square is a rectangle. A square is just a rectangle where the height and the width are the same. They're not necessarily different. In a rectangle, the height and the width can be different, or they can be the same. So this is a rectangle. This is a square. And a square matrix is an n by n matrix. When you write it out, it's a square. The number of rows equals the number of columns. So for example, a 2 by 2 matrix is an example of a square matrix, right? A, B, C, D, or A11, A12, A21, A22. These are 2 by 2 matrices, and you can always multiply them, and you get back a 2 by 2 matrix. So, in fact, you can say that for 2 by 2, so if you let, say, M22 be the set of all 2 by 2 matrices, first of all, it's a vector space under vector with matrix addition, but it's also it's a metric space with which also has a multiplication. So it's a little bit richer than just a vector space. There's a way to multiply 2 matrices and get back another matrix of the same shape. And if you take any matrix A, B, C, D, and you take what's called the identity matrix, 1, 0, 0, 1, A times I is always A, and I times A is always A. So this matrix is like the number 1. It's a multiplicative identity. And in fact, it's called the identity matrix. In general, if you have an n by n matrix, if the matrix has 1s down this main diagonal and 0s everywhere else, it's called the n by n, or the n-dimensional identity matrix. This is always sort of the multiplicative unit for matrix multiplication. Okay. Any questions so far? All right. Now, chapter 1, we dealt with linear equations. I just introduced matrices. They are very closely connected. Let me just look at an example. We talked about matrix multiplication. So suppose I have a matrix like 2, 3, minus 1, 5, and I multiply it by a vector, well, this. So a column vector is like a matrix. It's just a matrix with 1 column. This is 2 by 2. This is 2 by 1. You multiply them, you're going to get another 2 by 1 matrix. 2x1 plus 3x1 minus x1 plus 5x2. Okay. So this matrix times this column vector gives this column vector. So suppose we had, for example, the homogeneous equations, 2x1 plus 3x2 equals 0, and minus 1x1 plus 5x2 equals 0. We can write this system of equations in sort of like vector and matrix form. I could say this is the same as saying 2x1 plus 3x2 minus x1 plus 5x2. That vector equals 0, because 2 vectors are the same if their coordinates are the same. So to say that this vector equals this vector means exactly 2x1 plus 3x2 equals 0 minus x1 plus 5x2 equals 0. And this is exactly the same as saying that the matrix 2, 3, minus 1, 5 times the vector x1, x2 equals 0, 0. Another way of saying that is that a solution of this system of linear equations is equivalent to finding a vector x1 that solves this linear algebra vector matrix equation. Right? this and this are equivalent ways of writing the same process. If this were not 0, 0, if this was an inhomogeneous system, 2x1 plus 3x2 equals 7, and minus x1 plus 5x2 equal 3, then that's the same as saying that this vector equals this vector, or this matrix equation equals this. So you can rewrite a system of linear equations in vector matrix form. So a vector that solves this is the same as a pair of numbers that's a vector that solves this. Now, one solution of these equations is x1, x2 equal to 2, 1. Because if x1 is 2 and x2, if x1 is 2 and x2 is 1, you get 4 plus 3 is 7, minus 2 plus 5 is 3. And you can check if you take the vector, the matrix 2, 3, minus 1, 5, times 2, 1, if you do matrix multiplication, you get 2 times 2 plus 3 times 1, minus 1 times 2 plus 5 times 1. That's 7, 3. So this vector is a solution of this vector equation. So the general algebraic formulation follows very simply from this. Suppose we have a system of linear equations, n variables, and let's say we have m equations. So we have m equations in n variables. You can take the matrix of coefficients of the equations, call it A, which is the coefficients of the equations to give you the rows of the matrix, A11, A12 up to A1n, all the way down to AM1, AM2, AMN. And I can also look at the right-hand sides of these equations and write the vector B is going to be a column vector, B1 down to B sub m. And this set of equations is equivalent, if I write this in matrix form, this is equivalent to AX equals B, where X is x1 down to x sub n. It's this column vector of the variables. If you take the matrix A, multiply it by the column vector x1, you get a vector whose coordinates are the left-hand sides of these equations equal to the right-hand sides. So this is a way to convert or to rewrite a system of linear equations in matrix form. This vector B has m coordinates. This is in Rm. The vector X has n coordinates. This is in Rn. Right. Right. And sometimes we write what is called the augmented matrix. So this matrix A, you have m equations, so this has m rows. You have n variables, so you have n columns. This is an m by n matrix. The augmented matrix will have the same number of rows, but one more column, n plus 1. And the augmented matrix that corresponds to an inhomogeneous system of linear equations is the following. You write down the matrix A, and we have to add one more column, and the column is going to be the B's. So for example, if we have the system of linear equations, 2x1 plus 3x2 equals 7, minus x1 plus 5x2 equals 3, the matrix A that comes from this would be the matrix of coefficients of the variables, 2, 3, minus 1, 5. The vector B would be 7, 3. And the augmented matrix is this matrix with this column added. So 2, 3, minus 1, 5, 7, 3. So that's the augmented matrix for this system. Okay. Any questions so far? Now, what I want to do is translate the process, the algorithm of Gaussian elimination from equations to matrices. So recall, this is all very important. Two systems of linear equations are called equivalent if they have exactly the same solutions. And for systems of linear equations, we had three operations on systems of equations that produce equivalent systems of equations. So the first was interchange. You can interchange any two equations. Right? Just write the first equation as the third and the third equation as the first. Interchange two equations. Second, you can multiply any equation by a non-zero scalar. And third, you can add a multiple of one equation to another equation. All right. So these are the three, I'll call them elementary operations on a system of equations that produce equivalent systems. Now, suppose you take your system of equations and you write it in matrix form. Let's see. What corresponds? So let's write this. So let's translate this into elementary operations on the rows of a matrix. So to interchange two equations, again, and let's think of this. Suppose we sort of, well, we have in our heads the augmented matrix. Of the system. So you have A11 up to A1N, V1 down to AM1, AMN, B sub M. Right? The A's are the coefficients of the equation, the B's are the right-hand sides. So to interchange two equations simply means to interchange two rows. So one elementary operation on the rows of a matrix as to you can interchange any two rows of the matrix. To multiplying an equation by a scalar is the same as multiplying any row of the matrix by a non-zero scalar. And to add a multiple of one equation to the other corresponds exactly to add some scalar multiple of one row to another row. So these are the elementary row operations on a matrix. You can interchange two rows. You can multiply a row by a non-zero scalar, or you can add a multiple of one row to another. And notice each of these operations is reversible. If you interchange two rows, and then you interchange the same two rows again, you're back where you started. Like if you interchange rows 1 and 2, row 1, row 2, then you have row 2 first and row 1 first. And if you interchange these two rows again, you get row 1 on top and row 2 on the bottom again. You're back where you started. So this operation of interchange is reversible. If you multiply a row by 2 and then you multiply the same row by a half, you've canceled the 2, you're back where you started. Multiplying a row by a non-zero scalar is also reversible. And if you add a multiple of one row to another, you can get back the original matrix by subtracting that same multiple of the row to the new row you had gotten. So these are all invertible or reversible operations. And if you can get one matrix from another by elementary row operations, you have what are called equivalent matrices, certainly row equivalent matrices. So suppose, for example, I start with the matrix A, which is 2, 5, 9, 3. I claim this is row equivalent to the matrix B, minus 8, 7, 1, 6. Now, if you look at these two matrices, it's not at all obvious. You can get from this matrix to this matrix by some series of these elementary row operations. But in the notes, I actually put down a sequence of operations which carries this out. So let's see, suppose A is 2, 5, 9, 3. And then I add minus 4 times the first row to the second row. So this will give me a matrix, I'll call it A1. The first row doesn't change, but I'm taking the second row minus 4 times the first row. So 9 minus 8 is 1. 3 minus 20 is minus 17. So you don't have to ask, why am I doing this particular operation? This is simply some elementary row operation. I'm allowed to do it if I feel like it. Right? Then we apply another elementary row operation. suppose I take the first row, I don't change the second row, but I'm going to take the first row minus 2 times the second row. So 2 minus 2 is 0. 5 plus 34 is 39. Then I'm going to get another matrix where I'm not going to change the first row, but I'm going to add some multiple of the first row to the second. And for whatever reason, I'm going to multiply 23 over 39 times the first row. So if I multiply the first row by anything, I get 0, and adding it to 1 is still 1. 23 over 39 times 39 is 23. 23 minus 17 is 6. So I get this. Let me do another elementary row operations. I'm not going to change the second row, but I'm going to add a certain multiple of the second row to the first row. And I'm just going to multiply the first row by a scalar, 55 over 39. Why? I don't know. It's just a random choice, but it's okay. So if you multiply this row by 59 over 39, 0 times anything is 0. 39 times 55 over 39 is 55. Let me take this matrix, and I'm not going to change the second row, but I'm going to add a multiple of the second row to the first row, namely minus 8. So I'm going to take the first row minus 8 times the second row. So 0 minus 8 is minus 8. 55 minus 8 times 6 is 48. 55 minus 48 is 7. So this somewhat stupid sequence of elementary row operations is completely valid. I'm allowed to do this. And I get a sequence of matrices, each of which is equivalent to everyone else in the sequence. So in particular, this matrix A that I started with is equivalent to this matrix, which is exactly the matrix B. So this is some sequence of elementary row operations that goes from this matrix A to this matrix B. It doesn't solve any particular problem yet, but this is simply the procedure of carrying out elementary row operations. Okay. Any questions about this? So this is all sort of formal algebra. We're just, okay. So let's go back and apply Gaussian elimination to a sequence of equations, and then see how this would translate into doing the same operations, but in the matrix form instead of the equation form. So here's a system of equations. 9x plus 11y equals minus 1, and 5x plus 6y equals 3. And here I have the augmented matrix. So this augmented matrix, the coefficients of the equation 9, 11 become the first two coordinates in the first line. 5, 6, these are the coordinates of x and y in the equation. They become the coordinates 5, 6 for the second row. And then the right-hand side, minus 1, 3. So this is the augmented matrix that corresponds to this set of equations. Now, if I'm going to perform Gaussian elimination on the equations, the first step is to have the coefficient of x equal to 1. So I multiplied the first equation by a ninth. So this becomes x plus 11 over 9y equals minus 1 over 9. And the second equation didn't change. This is exactly the same as taking the augmented matrix and applying the elementary row operation of multiplying the first row by a ninth. I get 1, 11 over 9 minus 1 over 9, and the same second row. Okay. If I'm applying Gaussian elimination, then I'm not going to change the first equation, but I want to eliminate the x from the second equation. So I subtract 5 times the first equation from this. 5x minus 5x is 0. 9 minus 55 over 9. Sorry, 6 minus 55 over 9. 6 is the same as 54 over 9. So I get minus 1 over 9 y. 3, I'm subtracting 5. 3 minus 5 ninths. 27 minus 5. Sorry. Minus 5 times this is plus 5 ninths. 3 plus 5 ninths is 32 over 9. And so I eliminated the x. And in terms of my system of equations, or the augmented matrix, the first row doesn't change. And I added minus 5, the first row, to the second row, and I get 0 minus a ninth, 32 over 9. So here I'm performing elementary operations on the equations. Here I'm applying elementary operations on the rows of the matrix. I want the coefficient of y to be 1, so I just multiply this equation by minus 9. X 11 over 9y equals minus 9, doesn't change. Multiply by minus 9, I get y equals minus 32. Multiply the second row of the matrix by minus 9. I'm not changing the first row, but I get 1 minus 32. Then I want the coefficient of y in the first equation to be 0. I want it to disappear. So I still have y equals minus 32. I add to the first equation minus 11 over 9 times the second. So I get x plus 0. 11 over 9y minus 11 over 9y is 0. And I get minus 1/9 minus 11 over 9 times 32. So if I do my arithmetic, 11 times 32 is 352. If I add 1, I get 353 over 9. Oops. Let's see. I want to make sure I did my arithmetic correctly. X plus 11 over 9y is minus a ninth. Y is minus 32. If I multiply this equation by 11 over 9 and subtract, I get minus 1/9 minus 11 over 32 times 9. So that's minus 1 over 9 minus 11 over 32 times minus 32. So that's 32 times 11. Which is 142. Somehow my arithmetic isn't working out correctly. Let me just do it more carefully. So I have this system of equations. I want to get rid of the 11 over 9. So I take minus 11 over 9 times the second equation and add it to the first. So what I get over here is minus 1/9 minus 11 over 9 times minus 32. So that's 11 times 32 plus 1 over 9 with the minus sign in front. No, with a plus sign in front. It's this 11 over 32 minus 1. So 11 times 32 is 352 minus 1. So this becomes 351 over 9. And 351 over 9, divide this into this. This goes exactly 39 times. So I get x equals 39. And here I have 0, 1, minus 32. Again, if I add minus 11 over 9 times the second row to the first row, I get 1, 0, 39. So the solution of my system of equations is x equal 39, y equal minus 32. And this corresponding to this matrix is the system of equations 1 times x plus 0 times y equals 39. 0 times x plus 1 times y equals minus 32. Or simply x equal 39, y equal, or xy is equal to 39 minus 32. So the whole point of this exercise is, so by now you're supposed to understand thoroughly Gaussian elimination for a system of equations. We can perform the same algorithm instead of to the equations, to the augmented matrix of the equations, using the elementary row operations, and we get an equivalent way and sometimes a more efficient way of solving our linear equations problem. All right. So let me do another example. And the more examples you do yourselves, the better you will understand the material. So here we have 3 equations and 3 variables. 2x1 minus x2 plus x3 equals 6. x1 minus 7x2 minus 4x3 equals 0, minus 3x1 plus 2x2 minus x3 equal minus 1. So this is 3 equations and 3 unknowns. And we want to solve it. And in the notes, I solved it step by step using Gaussian elimination. But now I want to solve it using the augmented matrix. So corresponding to this system of equations is the augmented matrix. It's going to be a 3 by 4 matrix. The first row, 2, minus 1, 1, 6. The second row, 1 minus 7, minus 4, 0. The third row, minus 3, 2, minus 1, minus 1. So here we have equations. And here we have the augmented matrix. And I'm going to apply elementary row operations to try to end up with a matrix which is an equivalent in form to what we want to get by using Gaussian elimination. We want to have in each row, the first non-zero coordinate is a 1, and above and below it in that column is only zeros. And any rows that are all 0 are at the bottom of the matrix. And when we put the matrix in that form, we're done. We actually have solved our system of equations. So let's see. So here's our first matrix. Maybe to get a 1 here, I could multiply the first row by a half, but it's simpler just to interchange rows 1 and 2. So minus 3, 2, minus 1 doesn't change. The second row, I make the first row. And the first row I make the second row. So this is an interchange of rows 1 and 2. Then I want to get a 0 here and a 0 here. So let me do a step by step. The first row I'm not changing now. The third row I'm not changing now. But to get a 0 here, I can subtract twice row 1 from row 2. So 2 minus 2 is 0. Minus 1 plus 14 is 13. 1 plus 8 is 9. 6 minus 0 is 0. So I got my 0 here. Then I want a 0 here. So I'm not changing now the first row or the second row, but I add 3 times the first row to the third row. 3 minus 3 is 0. Minus 21 plus 2 is minus 19. Minus 8 minus 1 is minus 9. 0 plus minus 1 is minus 1. Okay, so now in the first row, the first non-zero numbers are 1, and in that column, everything else is a 0. Now I look at the second row, and I want to change this 13 to a 1. So I don't change the first row. I don't change the third row. I just multiply this row by 1 over 13. I get 0, 1, 1 over 13. Oh, this is a 6. No, sorry. That became 0, 6 minus 1. 0, 6 minus 1. This is a 6. I'm multiplying this by 1 over 13, and I get 6 over 13. Okay. Then I want to get a 0 here. So the second row, I'm not changing now. The third row, I'm not changing now. But to get a 0 here, I add 7 times the second row to the first row. So 0 plus 1 is 0. 7 minus 7 is 0. That's what I want. 7 over 13 minus 4 is 7 minus 52 over 13. Is that right? Oh, my writing is bad. This is a 9, so this is a 9. I'm multiplying this by 7 and 9. 63 minus 52 is 11. And 42 plus 0 is 42. 42 over 13. So now I have a 0 there. Then I want to get a 0 there. So I'm not changing the first row. I'm not changing the second row yet. But I add 19 times the first row to the second row, to the third row. 0 plus 0 is 0. 19 minus 19 is 0. 19 over 13 minus 9. This is 9 over 13. I don't know why I keep writing this down incorrectly. This is 9 over 13. This is 9 over 13. Okay. So I'm multiplying this row by 19 and adding. So 19 times 9, 171. Minus 9 times 13 is 1. I just have to do, I'm not using calculator, I'm trying to do everything by hand. So here I have 1, 0, 11 over 13, 42 over 13. 0, 1, 9 over 13, 6 over 13. And 0 minus 19. Okay, let me go back to, I made some arithmetical error and I always like to fix these things up. So let's say here I have 1 minus 7 minus 4, 0. 0, 13, 9, 6 minus 3, 2 minus 1, 1. Then I'm not changing the first or the second rows. I add 3 times the first row to the third row to kill the 3. I get a 0. And I get 0. 3 times this is minus 12 minus 1 is minus 13. Minus 19 minus 13 minus 1. All right. Here I just didn't change the third row, so this is still a minus 13. And this is still a minus 13. But I multiplied this, I did by 1 over 13. Then I eliminated the 7 by adding 7 times this row to the first row. So I got 1, 0, 11 over 13, 42 over 13. 0, 1, 9 over 13, 6 over 13. And 0 minus 19 minus 13 minus 1. Okay, so this is okay. Then to eliminate the minus 19, I haven't changed the first 2 rows. I add 19 times the second row to the third row. Minus 19 plus 19 is 0. I have 19 times 9. Minus 13. So that's 171. 13 times 9 is 117. What is this? This is 19 times 9 over 13 minus 13. So 19 times 9 is 171. 13 times 13 is 169. The difference is 2. So this is 2 over 13. And 19 times this, 6 times 19 over 13 minus 1. 6 times 19 is 154 over 13 minus 6 times 19 is 114. 114 minus 13 is 101. So this is 101 over 13. Again, this is all done in the notes. In the notes, I mean, it's correct. And this is correct. I'm just have to do my arithmetic by hand carefully. Okay, I have 0, 1, 0, 0, 1. The first 2 columns are great. I want to make this a 1, so I multiply this row by 13 over 2. I get 1, 0, 11 over 13, 42 over 13. 0, 1, 9 over 13, 6 over 13. I multiply this row by 13 over 2, I get 0, 0, 1, 101 over 2. Okay, good. And then I need to eliminate these 2 numbers. So to turn this into a 0, so there are going to be 2 more steps. I'm not changing the second row yet. And to the third row, I subtract 11 over 13 times the second row. 1 minus 0, 0 minus 0, 1, 0. 11 over 13 minus 11 over 13 is 0. And then I have 42 over 13 minus 101. See, I'm multiplying this row by 11 over 13 and subtracting. So 42 over 13 minus 101 over 2 times 11 over 13. So what is that? If I do it by hand, not necessarily the best thing to do, but what the hell? I get how to do arithmetic. So it's 42 over 13 minus 11 over 13 times 101 over 2. So that's equal to 1111 minus 42 and minus that over 13 times 2, 13 into that. It's much simpler if I used a calculator. I'm just not using a calculator. I mean, I know what the answer is because I did it carefully and I didn't put it in the notes, but why can't I get my arithmetic to work? I want to eliminate this 11 over 13. I have 11 over 13, 42 over 13. 101 over 2. So I'm multiplying this by a minus 11 over 13 and adding it to that. So minus 11 over 13 times 101 over 2 added to 42 over 13. So that is 84 minus 1111 over 2 times 13. 11 take away 4 is 7, 10 take away 2 is 2. 0, 1. If I divide that by 13, it's 7, 1, 1. And if I divide that by 13, I get 9. Oh, okay, good. So I did my arithmetic correctly, minus 79 over 2. And then the last step is to get rid of this 9 over 13. So I have 1, 0, 0, minus 79 over 2. Third row is 0, 0, 1, 101 over 2. And here I have to subtract 9 over 13 times the third row from the second. So I get 0, 1, 0. And here I get 6 over 13 minus 9 over 13 times 101 over 2. what is that? That's equal to 12 minus 999 over 13 times 2. That's minus 987 over 13 times 2. Let's see, 13 into 987. Does that go evenly? Let's see. 7 times this is 91. So 77. You have to kind of like arithmetic to want to keep doing this by hand, but that's okay. So this is 6 over 13 minus 9 over 13 times 101 over 2. That's 12 minus 999, which is 987. Seven threes are 21. 9 threes are 27. Off by a 1. I don't understand why this is off. According to my notes, when I did the calculation, I get minus 69 over 2. So let's assume this is okay, and I'll check it later because I don't want to spend too much more time on this. But this is the process. This is using elementary row operations on a system of equations to get the answer, to solve your equations. And in the end, what is the, when we do, so we perform the goal. The goal is to transform the augmented matrix into a form which gives us a solution to our system of equations. So we want to do Gaussian elimination by means of the augmented matrix. And the idea is to perform elementary row operations on the matrix to obtain an equivalent matrix in what is called row-reduced echelon form. Perform elementary row operations on a matrix to obtain a matrix in row-reduced echelon form. And a matrix in row-reduced echelon form has the following shape. So A is a non-zero m by n matrix. And it's in row-reduced or row echelon form, if it has the following properties. So first of all, you could have rows that are all zero. So the zero rows are at the bottom. Well, that's easy. Whenever you obtain a zero row after some elementary row operations, if it's not already at the bottom, switch it with something to put it in the bottom. That's easy. Second, in each row, in each non-zero row, the first non-zero coordinate is a 1. So in any given row, you might have some zeros, and then your first non-zero coordinate is a 1, and then you have other stuff. And above and below it are zeros. So in this column, you have a 1 and everything else is a 0. And the third condition is that so every non-zero row starts with a 1. And as you move down the matrix, down the rows, the non-zero ones move to the right. So here's a row. In the next row, the non-zero 1 is in a column to the right of this, and so forth. So in each non-zero row, you start with a 1, everything above and below it is 0. And as you go from one non-zero row to the next, the 1 that you see is to the right of the one that was in the previous row. That's row reduced echelon form. And the theorem says it's that through elementary row operations, you can always put a matrix in row echelon form or reduced row echelon form. Like this is really the thing. Okay, so there should be a lot of homework for Friday. On matrices, and the more you do, the better. Okay, wow. All right. That is all we're going to do today. Any questions before we quit?
Yeah, Professor,
Yeah.
can we write our systems of equations in augmented matrix form for the midterm?
So the answer is you have to answer the question as it's stated. So there will definitely be one question where I give you a system of equations and ask you to perform Gaussian elimination step by step. So the best way, I mean, the simplest thing is just to use the equations. But I guess if you can do the same thing step by step with the matrix, that's okay.
Okay, awesome.
But it's all, I mean, the algebra is exactly the same in both cases.
Yeah.
Yeah. Okay. Any other questions? Okay, again, I remind you, I have office hour at 7 o'clock tonight. Welcome to come and ask questions. Okay. Bye all.